All right, now that we're all pros in our respective trends, let's get to the presentation part. So, atomic radius. Who's doing atomic radius? All right, go for it. What's the definition of atomic radius?
May be defined as one half the distance between the nuclei of identical atoms bonded.
Half distance between two nuclei. Okay. This is also known as size. Okay, also known as size. What happened to my focus here? This is also known as size. The half the distance between two nuclei that are bonded together, that is how they come upon this information. But what you're really describing is how large that atom is. That's what you're really getting at, how big that atom is. Now, in terms of drawing arrows to describe the direction in which the period trend increases, what direction am I going to draw my arrow? It decreases from left to right. So since I asked you to draw an arrow to indicate the direction it increases, what direction is your arrow going to point? Yeah, 'cause you guys just told me that atomic radius decreases from left to right in a period. Yeah, you're right. And then what I'm wanting you to draw on your piece of paper is an arrow pointing the direction of the increase. You guys follow it? Now, both bits of information, they're correct, right? They're correct. I can say just as correctly that the radii of atoms increase as I go to the left, as if I were to say the radii of atoms decrease as I go to the right. Both are true. Both are accurate. Both are the trend. But realize I'm just saying from left to right versus from right to left. Okay? The trend is still the trend. Just depends on, what direction you're looking at. All right, now what's the group trend for atomic radii? Yeah, so I'm going to draw my arrow this way. So that means the single largest atom on the periodic table in terms of atomic radius would be this guy. Real big. Real big. But here's the thing. Why? Why is this the case? So what did you guys come up with? Okay, so as you go across a period, you're increasing the amount of positive charge in the nucleus, right? And what's changing in these nuclei that the amount of positive charge would increase as you go to the right in a period? What's going up? Number of protons, right? So the number of protons is going up by 1 each time you move to the right, one element. So that means the overall amount of positive charge is also going up. Cool. In addition to the protons, the number of electrons are also going up. So not only am I increasing in the total amount of positive charge that is in the nucleus, I'm also increasing in the total amount of negative charge. And so if I have a stronger positive charge and a stronger negative charge, what do you think is happening to my overall attractive force? It's way stronger. It's way stronger. And so if the attractive force with the electron cloud is becoming stronger, you're going to pull those electrons in more strongly. And if you're pulling the electrons in more strongly, they're closer to the nucleus, right? Doesn't that make a smaller atom? Right? So the cause is, as you increase the number of protons and electrons, overall effective nuclear charge increases increasing the attractive force. All right, so this is your period trend. This is why the period trend is the way it is. Now, for the group trend, if we remember our quantum numbers, okay, we have the principal quantum number 1, 2, 3, 4, 5, 6, 7, going up by 1 every time we go down one group. You guys remember that from chapter 4? Right, principal quantum number? That's an energy level. Okay, it's a layer of electrons in the atom. So each time you go down a group, you are increasing the number of energy shells in the atom. And if you increase the number of energy shells, just like if you were to increase the number of stories in a building, the building gets taller. When you increase the number of shells in an atom, that atom is getting larger. And so that's the period trend and the group trend for atomic radius.